Welcome back to the classroom. My name is Mr. Wong, and in today's lesson, we are going to be looking at solving for how forces are drawn and interact on an inclined plane. I'm going to start firstly by looking at how the normal force looks on a flat surface, and then we'll compare how the normal force changes as we increase that angle of incline from the horizontal, and what type of force components come from that, and how does that affect an object on an inclined plane.
So the weight and normal force, if you're on a flat surface and the object is stationary, then the weight force and the normal force are essentially in equal and opposite or equal magnitude but in opposite directions. Okay? Mathematically speaking, you can create a little formula for that. You can write it like this. Fg, gravitational force, equals to mg minus the normal force. The minus just means it's in the opposite direction. So it means opposite direction. What you'll also find is these little arrows on the top. This indicates it's a vector. As we know, force is a vector. Acceleration due to gravity is also a vector. So we're essentially saying that Fg is equal and opposite to the normal force if the object is on a flat surface. This does change, however, if you tilt it at an angle. Okay, it looks like this now. No longer is F net pointing in the opposite direction of Fg, but just so you know, Fg will always point directly down. F net or Fn, F normal always points perpendicular or at 90 degrees to the surface. So that's what it looks like there. This is what I was alluding to. What we actually find is the normal force and gravitational force, if they are in opposite or slightly different directions, not direct opposites to each other, then you might create a net force for the object. And that's why when you place an object on a slope, it might slide down because of this indifference between the normal force and the weight force. And so what do we have here? The component of the weight force will act parallel to the surface, will cause the mass to slide down. So there's that there, and the normal force will be a component of the weight force. What does that actually mean? Let me show you through a little sketch. So let's just start here. So we have an inclined plane at an angle theta. We have our object. Let's just ignore that object for now, pretend it doesn't exist. We have a force pulling it down. That is Fg. And Fg is given by the mass times acceleration due to gravity. So we draw it along like that. Okay? So that's first step of what we know. We also know that at the same point where Fg is, F net is going at 90 degrees from our surface, or Fn, F normal. The normal force is going at 90 degrees to our surface, out, up, that way. If I try and work this out, I can assume that Fg has gone straight down from the slope to our imaginary line here at 90 degrees. Okay? So I've essentially drawn a triangle. What I also know is at this angle here would be 90 degrees because of this part here minus theta. So this is 90 minus theta. So that's stage 2 of our graph. if I want to find the component of my normal force, imagine I draw another line that comes out like so. Okay, so this is just the reverse of the normal force, but it will come in handy. And as you know, the normal force is always 90 degrees to a surface. So obviously the other side is also 90 degrees, which means this angle here that I'm writing in here is theta. What we have here, I'll say that again, because it's 90 degrees, or the normal acts 90 degrees to a surface. So if we look at one side of the normal force, it's 90. We already know on this side it's 90 minus theta. So the other unknown angle would have to be theta. So that's that side. If I try and connect minus Fn to Fg, and assuming I'm crossing this at a perpendicular angle, so I'm cutting it at right angles as well, this will be 90 minus theta. And this will be, let's call it F forwards or F net, whatever you want to call it right now, F forwards. Now, if you look at where F forward is on this graph, it is exactly the same position as the F net in our diagram on the left. So I can just write F forward this way. Okay? Now, if you don't quite understand how we got all of those arrows together, please feel free to replay this part of the video again. Once you do understand how it works, it actually becomes really handy and powerful in terms of the questions we go through later. Okay, so I want to firstly work out what is the normal force in this equation. The normal force here is just a component of the weight force. Why do I say that? Have a look here. Okay. We have theta, so we know that theta is there, so we can use a trig ratio. We have this component, which essentially acts as the adjacent side. We have this component of Fg coming down this way, and that's the hypotenuse. So we know that if it's adjacent over hypotenuse, in this case, Fn over Fg. The only reason why I'm writing Fn is just so to make things simpler. You can write it as a negative if you want to show the different direction, equals to cos theta. So if I want to find my Fn component using Fg, Fn equals to Fg cos theta. So the next part we're going to look at is for our forwards motion. Our forwards motion. This is the opposite side. This is the hypotenuse. Okay? So we have the opposite side over the hypotenuse, which is F forwards over Fg. Sine theta is the trig ratio we're using here. If I want to write it out as a function of what F forward is, F forward is Fg sine theta. Okay, so there you have it. This is how we can find the force of an object falling down an inclined plane using the component or using its weight force component, and how we can find the normal force acting on that object using the weight force component again. So that's just to show you as a diagram and transition of what happens. Please make sure you copy this down into your notes. Okay. And so we'll move on. As you can see here, we have a couple of additional, well, it's exactly the same thing, but I just want to show you this stands for the weight force. So W vector arrow stands for the weight force. You can write it as Fg. The reason why I'm not going to suggest you to write capital W is because we will come across a scalar quantity called work done, which looks at the change in energy, and that is also in capital W. So from now on, just make sure weight force is Fg, not capital W. You might also see a thing called Fk. We will go through this a bit later, but this is actually the friction force. Or this is.
That concludes the first part of solving forces on an inclined plane. Our next video, we're going to be looking at solving the problems based on these scenarios that we've talked about in this video.